Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we continue with our discussion on definite integrals. So again, walking through that doorway into Calc 2, integral calculus that is. And in this video, we're going to continue with evaluating definite integrals using limits. So you should have watched my video at least on the definition of the definite integral because you're going to need that here. Before we go evaluating definite integrals using limits, we do want to recall what it means to use the left endpoint method versus the right endpoint method versus the midpoint method. Remember, you're given an ith interval. So we have an interval that goes from x sub I minus 1 to x sub I. And if you're going to use the left endpoint, you're going to basically take a sample point. So x sub I star is a sample point within that interval. In fact, let me say it this way. X sub I star is an element of that interval. Now, a lot of people wonder why I'm such a huge fan of the x sub I star notation when often all we do is use right endpoints or left endpoints or midpoints. And the reason why is because I'm an applied mathematician, both a theoretical and applied mathematician. But in my applied mathematician side, I know the real use of integration in the real world. And we rarely use right endpoints or left endpoints. We actually use a variable point. So sometimes a third of the way through, sometimes a tenth of the way through. It just depends on how quickly the function is changing on an interval. And so this is why I'm a fan of the x sub I star notation. Now, if you're using the left edge point, then x sub I star would be that point right there. If you're using the right edge point, well then, there's your x sub I star right there. And that's what I say over here on the right-hand side. If you're using a midpoint, you just average the left and the right endpoint values. That's it. So now let's go ahead and jump into some examples. I like this kind of introduction where we slowly go in. It's going to feel like a review of previous material we've talked about, but that's super important because this high level material, you want to see it over and over again as much as possible. So we have this definite integral. Somebody just walks in the room, they say, hey, I've got this integral. It has a lower limit of 0 and an upper limit of pi over 2, and that definite integral I'm taking of the cosine to the 4th power of x with respect to x. You say, okay. And you tell them, well, I don't quite know how to evaluate that right now, like quickly, but I can approximate the value because I know that all this is the limit of a Riemann sum. And the Riemann sum could be a right endpoint method, a left endpoint method, or a midpoint method. So we could say if we were using the midpoint method, it'd be the summation I equals 1 to n of our function evaluated at the midpoint of each slice. And that would just be the average of each subinterval, delta x. Okay. But in this case, I don't have all my life to add up a bunch of values, right? Because that would be an infinite number of values I'm adding up. So instead, I'm going to approximate this just using 4 slices. So you just let them know ahead of time that this is going to only be an approximation. With n equals 4, you can easily find out what delta x is. Remember, delta x is b minus a over n. b is pi over 2. a is 0. Again, n is 4. So this can be pi over 8 is what our delta x is. And then x sub I, you actually don't need to do this if you're only doing 4 steps, but I'm just going to go ahead and showcase this. X sub I is a plus I delta x, and that would be a, 0, plus I times delta x, which is pi over 8. So that's just pi over 8 times I. That would be our x sub I. Now, if I'm going to approximate this definite integral using m sub 4, which means midpoint method with 4 slices, okay, then that is going to be, well, this is essentially the midpoint method. Oops. This is the Riemann sum for the midpoint method right here. And we only want to go to n equals 4. So I'm just going to copy that notation. I'm going to say that's the summation I equals 1 to only 4 of f of x sub I minus 1 plus x sub I over 2 times delta x. Now, if you're doing this by hand, to be honest with you, there are faster ways than what I'm about to show you. But I'll just show you kind of a nice way to do this. In fact, maybe I should label them as 2 separate methods, because one's going to be helpful if you're doing a midpoint method with 1,000 slices, and the other one's just going to be helpful if you're doing a short number of slices by hand. And let's do the short number of slices by hand first. So let me label this way number 1, small n, and you're doing things by hand. So small number of slices, you're doing things by hand. The way you're going to do this is you'll find out what the midpoint is for the first interval. Whoops, that was supposed to be 1 there. So find step 1, find, you know what? Let me move this off to the side and then I'll write that find. Okay. Find the midpoint for the first subinterval. And that first subinterval has a left endpoint of x sub 0 and the right endpoint of x sub 1. So you just compute that. Now remember, x sub 0 is where we're starting. X sub 1 is, well, I could just quickly grab that. X sub 1, you let I equal 1 right there. It's pi over 8. And divide that by 2. That's pi over 16. So that's our very first sample point. Okay, so I'm going to call that x sub 1 star. That's our first sample point. Well, if you have a small n and you're doing this by hand, remember that everything really, if you're slicing up an interval into n sub intervals, everything's a distance of delta x away from each other. Delta x, delta x, delta x, delta x, right? Well, that includes the midpoints actually. So if that's the midpoint right there, to get to the next midpoint, it is actually a wiggle of delta x. So to get to the next midpoint, I'm just going to take that last midpoint and I'm going to add the step size, which is pi over 8, or 2 pi over 16, which would be 3 pi over 16. And then I can get to the next midpoint, oops, so 3 star, by adding to that 3 pi over 16 another step size of pi over 8, which again is 2 pi over 16, which means you'll have 5 pi over 16. So this is kind of a nice way of doing it. And then the fourth and final step, because we only have 4 slices, is just going to be 7 pi over 16, again, because you're adding 2 pi over 16 because of the step size. So that's an easy way to do it if your n is small and you're doing everything by hand. This is not the way to do it if you're using a computer. But in this method, I can then go up here and I can just say, okay, great. Well, let me go ahead. First of all, the delta x we all know is pi over 8. So I'm going to factor that out front. And then what I'm going to do is evaluate my function, which is cosine to the 4th power. I'm going to evaluate that all those midpoints. So cosine to the 4th power of, I forget already, pi over 16. And then plus cosine to the 4th power of the next midpoint, which is 3 pi over 16. And you get the idea. So let me just do that. Now, important to remember, when you grab a calculator for this, it should be set in radian mode. Very important, because calculus pretty much only works in radian mode. So that would be our approximate value. I should probably evaluate that. There we go. I just used Desmos off on the side. So 0.589. Now, I told you there's 2 ways to do that. That's the easiest way. Just do it that way if you're doing it by hand. However, let's suppose that instead somebody said, I want to use midpoint method with 20 slices or something like that. So you have a homework problem, or maybe you're using this in an industry and you need to actually do more slices than something that's feasible by hand. How would you do that? Well, you go back to this formula. Everything's set up properly here. But what you want to do is you want to find what we call a closed formula for what x sub I minus 1 plus x sub I being divided by 2 is. So remember, x sub I is pi over 8 times I. So you could, let me write this down as the second way. So this is if you have a large large number of slices, and you have to use a computer. You're gonna, step 1, find, notice by the way in the other problem I wrote step 1 and then I didn't have anything else. Sorry about that. So in this case, you're gonna find an expression for, well, first of all, I'll say for x sub I. And then 2, you're gonna find an expression for x sub I minus 1 plus x sub I minus 1 plus x sub I over 2. Now, we know that x sub I in this case is pi over 8 times I. So we have something plus pi over 8 times I. That something is actually x sub I minus 1. So pi over 8 times I minus 1. And that's all over 2. So now if you simplify this down, you get pi over 8i plus another pi over 8i, or in other words, pi over 4i, minus pi over 8, and this is all over 2. And now I'll just divide everything by 2, and you get that this expression is going to be pi over 8i minus pi over 16. And that would be my average value expression. So I would go to a computer. Let's say we want to do m sub, well, it has to be m sub 4 in this case because that's what we base this off of. But we could say m sub 4 is the summation I equals 1 to 4 of f, and instead of x sub I minus 1 plus x sub I being divided by 2, I just replace that with pi over 8 I minus pi over 16. And then remember, the delta x in this case is pi over 8. But then all I really need to do is plug in I equals 1, 2, 3, and 4, and you're ready to go. So that's how you would do it if you're using some type of computer or whatever. But generally, when you're doing it by hand, just find the first midpoint and add delta x's. That's the easiest way to do it. On to the next example. Consider the function f of x equals x squared minus 4x plus 4. We're going to graph this. I'll just graph it by hand, and then use 7 rectangles using right edge points to estimate the value of the integral from 1, the definite integral from 1 to 8 of that function. So off to the side, note that this actually factors as an x minus 2 quantity squared. So that's going to make it much easier for us to graph. Note that I didn't bother graphing it too far to the left because we're only concerned about the definite integral from 1 to 8. And remember, the definite integral, and that's the whole point of me saying graph this first, the definite integral is equivalent to the Riemann sum, right? And the Riemann sum is essentially the area underneath or between the curve and the x-axis. So really what we're asking when we're asking for the definite integral from 1 to 8 is we're asking what is the area underneath this curve from x equals 1 all the way over to x equals 8. It should be fairly large because, well, there's a ton of area there, right? So we're trying to find that full height or shaded area there. And we're going to approximate that using 7 rectangles. So the integral, I'm going to actually rewrite the integral here. The integral from 1 to 8. I just want you to see that handwriting. It's very important to constantly see that handwriting. So that's going to be equal to the limit as n tends to infinity of the summation I equals 1 to n of f at something delta x. And that something is dependent upon where we take our sample points. Well, if you're doing a right edge point, which is exactly what we're using, then it's x sub I. And we are going to approximate this using r sub 7. And r sub 7 is equal to the summation I equals 1 to 7 of f of x sub I, right endpoints, delta x. Now, I do want to mention something here. When you take the limit as n goes to infinity, it doesn't matter if you're using right, left, midpoints, 1/10 points, quarter points, doesn't really matter, actually. As n goes to infinity, all of them tend to the same value. So that's why most of the time when you see a Riemann sum, it's written with x sub I, because when you take the limit as n goes to infinity, it actually doesn't matter which edge point that you're looking at. And so it's very easy to work with right edge points. That's the preferred method, honestly. Although for approximations, it's not the best method, but at least for integration, it is. All right, so let's go ahead and figure out what x sub I and delta x are. So delta x is b minus a over n. That's 8 minus 1 over n, or in other words, 7 over n. Remember, we're doing 7 slices here, though. So n is equal to 7, and that will imply that delta x is equal to 7 over 7, or 1. That's super nice. And then x sub I is going to be, let's see, a plus I times delta x. A in this case is 1 plus I times delta x, which is also 1. So I'm going to insert this in here. This is a summation I equals 1 to 7 of f of, let's see, 1 plus I times 1. Not bad. Now, if you were to do this by hand, which I'm assuming they kind of want us to do this by hand. By the way, I didn't write delta x because delta x is 1. If you're going to do this by hand, it's going to be a lot of handwork, right? This is going to be when I is equal to 1, I'm going to go to my function. Remember, my function is f of x is equal to x squared minus 4x plus 4. This is not fun to do by hand. I'm going to showcase what it looks like. When I is equal to 1, it's going to be f of 2. And then when I is equal to 2, it's f of 3. ... until you get to I equals 7, which is f of 8. And then what we're going to do is plug those values into our function. And that is where it's nice to use something like Desmos or whatever, because this is just going to be a bear. Nobody wants you to do this all by hand. It's not like it's impossible. It's just not fun. Okay. But something that you can do here to speed up computations is the following. So let's suppose that you want to, instead of writing it this way, you could totally do that. By the way, you would not be wrong for doing it that way, the way I was just about to do it. But let me just showcase something to you so that you can actually see what's kind of cool about knowing the properties that we wrote down 2 videos ago. All right, so if I evaluate my function at 1 plus I, it's going to be 1 plus I squared minus 4 times 1 plus I plus 4. I hope everybody agrees with that, right? Well, what you could do is you can actually clean that up. You might say, no, forget about it. I don't want to go through all that mathematics because I would rather just grab my calculator and do all this. But let me just showcase how nice it is when you do this. This binomial, when you square it out, is 1 plus 2i plus I squared. And then we have a minus 4 minus 4i and a plus 4. Notice a lot of things clean up here. Summation I equals, it's supposed to be an equal sign and a summation. Everything just got erased. Sorry about that. Summation I equals 1 to 7. I'm going to write it in descending power order. So I squared. Let's see, we have 2i minus 4i minus 2i and a plus 1. And I don't know if you recall, you should, but we had these properties written before, and we're going to be using them now. So let's go ahead and see how that works. As long as the summation is finite, you can split this. So this is the sum I equals 1 to 7 of I squared minus 2 times the sum. Notice how I did that. I immediately factored out the constant. I equals 1 to 7 of I plus the summation I equals 1 to 7 of 1. Again, we have formulas for all three of these summations. The summation of I squared, for example. Well, we have just seen that. Let me actually bring that back. The summation of I squared is going to be sum from I equals 1 to n, will be n times n plus 1 times 2n plus 1 over 6. In this case, we're going to 7, so it's going to be 7 times 8 times 15 over 6. So this summation right here is going to be 7 times 8 times 15 over 6 minus 2 times the summation of I is n from I equals 1 to n would be n times n plus 1 over 2. So that's 7 times 8 over 2. So minus 2 times 7 times 8 over 2. And if you add 1 to itself 7 times, that's 7 times 1. Now, that is much faster than going through and saying, what's f of 1 and f of 2 and f of 3 and f of 4? This is where mathematics can really play some wonderful quick tricks for us. So 2's canceled there. 3 goes into 15 5 times, and the 2 goes into 8 4 times, and now we're ready to go. So let's see, that's 20 times 7, or 140, minus 56 plus 7, so minus 49, that's 91. And unless I made an arithmetic mistake, that is correct. So this is the approximate area underneath that curve, x squared minus 4x plus 4, from x equals 1 to x equals 8. That's the approximate value of this integral. It's roughly 91. Now, if you actually try to find the true area underneath this curve, it's much less than that. But because we're using right endpoints on an increasing function on this side over here, we're going to have a huge overestimate. But still, it's a decent, it's actually not too decent, but it's an estimate. How's that? And that finishes this evaluating definite integrals using limits video. In the next video, we'll jump forward and we'll start talking about properties of definite integrals.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.